Hi, my name is James Walker, and my mentors this summer were Professor Sunjo Chung and Kai Matsuka. My SURF project was the integration of distributed multi-agent localization for large-scale formation flying. Formation flying for aerospace is defined as the disciplined flight of two or more spacecraft. Real-world examples of formation flying include military pilots performing formation flying in jet aircraft such as the Blue Angels, or the flight patterns of migratory birds. Recently, formation flying has been applied to spacecraft and satellites. These distributed systems allow for more widespread use of micro, nano, femto satellites. For constellations of formation flying spacecraft, there are two main types of systems. The first is a system where there is a chief satellite in the constellation where each of the other deputy satellites talk to and transmit information to the chief, which then either translates that data or transmits it down to a ground station. One of the issues with this type of system is that if this chief craft is damaged in any way, the whole mission is compromised because the entire system relies on this one spacecraft. Another type of system is called the distributive system or a decentralized system. In this case, each craft communicates with each other. Therefore, none rely on one individual spacecraft. This type of system is much more complicated, but it allows for a mission to continue if a craft is damaged, because even if that craft falls out of usage, the whole system will still be able to function relatively well. The overall goal of my project is to support the guidance, navigation, and control analysis for formation flying missions. I was tasked with creating a program that would allow us to test the feasibility of upcoming formation flying missions. The first step to the project was to create a high-fidelity force model for perturbations during an orbit, and to develop this within MATLAB. This will be useful because it allows us to accurately model a spacecraft orbit while including common perturbations found by spacecraft such as J2, spherical harmonics, and atmospheric drag. The second part of the project was to develop a controls algorithm that will maintain passive relative orbits while doing maneuvers for constellations. Now this will involve readjusting orbits because of these perturbations affecting the orbits of the multiple spacecraft in a formation flying constellation. Because the spacecraft are not occupying the same space, they'll be experiencing perturbations slightly differently, especially drag. Therefore, as the mission continues, these spacecraft will start to deviate from their program path. So one of the purposes of this project is to create a way to simulate readjusting the orbits to what was originally desired. Another purpose is that if the constellations need to perform maneuvers in space, such as reorganizing the constellation around some unknown object or orbit, we would be able to do that while still maintaining our control over the system. The first step was to develop the high-fidelity orbit model. This orbit model will account for multiple perturbations that are often experienced during orbit. The particular ones chosen were J2 perturbations, spherical harmonics, and atmospheric drag. These are images generated from the software that I developed. On the left image shows the two orbits relative to a scaled model of the Earth, and the right is without the model. As you can see, there are two lines. One is a chief spacecraft, which is much larger and heavier than the deputy spacecraft. The deputy spacecraft is much smaller and lighter. You can see by the orbits that the black line, which is the chief spacecraft, is much less affected by the perturbations, while the smaller, lighter spacecraft has a much larger precession from an undisturbed orbit. Earth is not a perfect sphere. Due to the rotation of the polar axis as well as local variations in density and large geographic features, the true shape of the Earth is slightly oblate. This means the mass distribution is not perfectly uniform. Therefore, the gravitational field is also not uniform. The location of a satellite relative to the Earth's equator affects the applied gravitational forces. This can be seen on the image of the right, which shows the gradient of the Earth's gravitational field relative to the location on Earth. One thing you will notice is that the gravitational field seems to be stronger at the poles and weaker at the equator. This, however, can be modified using spherical harmonic functions to solve the Laplace equations. These functions are similar to Fourier analysis adapted to a spherical surface. These spherical harmonics can be superposed upon each other and then used to represent and analyze the physical properties of the surface of the Earth. The acceleration caused by the mass distribution is dependent on latitude, longitude, and radius of the spacecraft relative to Earth. This means Cartesian coordinates must be converted to spherical coordinates before anything can be solved. The program takes these x, y, z coordinates and converts them into the spherical frame. This allows us to apply the spherical harmonic equations to then model accurately the gravitational field of the Earth. The other important part of the high-fidelity orbit model was including atmospheric drag. Now, it is often approximated that that upper atmosphere has no drag, but this is actually false. There is low-density air at high altitudes, so when we're working with small satellites, such as the ones used in common formation flying missions, this drag needs to be accounted for. The drag force can be modeled using the typical drag equation. But in order to use that equation, we need to have a coefficient of drag, an air density, a velocity, an area, and a mass. Now the area, mass, and velocity will all be known for the spacecraft based on the initial specs of the spacecraft and the velocity given through the orbit model. So what we need is the coefficient of drag and the air density at each location in space. Typically, for a low Earth orbiting satellite, the coefficient of drag is used as 2.2. So that is what we used for our model. Now the density of air is more tricky because air density varies on a great many of things. So for this, we use the Harries-Priester model. The Harries-Priester model is used specifically for its increased accuracy and its computing efficiency. This model is based on several tables that account for the density of air measured throughout the solar cycle. Each of these densities is found at a specific altitude and solar flux value. Interpolation is then used to determine the maximum and minimum densities at a specific time. Solar flux data is recorded at a wavelength of 10.7 centimeters and gives an indication of the effects the sun has on the density of air. As the solar flux increases, the air density also increases. This is due to the increased heat energy which causes thermal expansions of the air particles. For this model, the solar flux being used is collected and reported by NOAA. The data has been recorded since 1957 and is still up to date in 2020. Using the reported solar flux data, the approximate sub-model from the Harries-Priester can be used to accurately predict the atmospheric density. One caveat of using the observed data is that there must be a date for that day. Therefore, we are modeling missions based off previous days. Now this is all right because based on a solar cycle, one orbit of the Earth and the Sun, the solar flux will be relatively the same because we stay the same distance away from the Sun. However, there is that little caveat of we won't know exactly what the solar flux will be on that day, but because the change will be minute and the effective drag on the spacecraft will also be small, the error experienced will not affect the data. This model was tested against data reported by the MSISE 90 model of Earth's upper atmosphere, differing across different levels of solar flux, high, medium, or low, and across each of those different altitudes available and the different solar flux concentrations, the density of the air was reported to be similar as the data that we collected using our model. Therefore, we can say that this model can accurately depict the density of air at these different altitudes. For the PRO maintenance algorithm, we first must be able to accurately model the orbits of the spacecraft, and to which we'll use the high-fidelity orbit model. But now we need to be able to represent the orbits of the spacecraft in relative coordinates. This is because the way we're going to implement the PRO maintenance program is in the terms of these relative orbital elements. So we must be able to represent the orbit in these elements. In this case, we will have a chief spacecraft whose orbit is defined by standard orbital elements. We will also have a deputy spacecraft That's orbit is defined by that Chiefs, and it will be defined by these relative orbital elements. There are 6 relative orbital elements. Delta lambda, which is the distance in the cross-track direction, also known as the drift term. Delta alpha, which is the relative semi-major axis. Delta EX and delta EY, which is the relative eccentricity vector in the x and y directions, and then the delta IX and delta IY, which is the relative inclination vector in the x and y directions. The image on the top shows the method for determining these relative orbital elements given the orbital elements of a chief and deputy. When it comes to actually showing these orbits in MATLAB using the graphs, it is very difficult to do this in terms of relative orbital elements. So what we want to do is convert these into relative position and velocity vectors, which we can then easily show. But the relative position and velocity vectors are shown by the algorithms on the bottom, and these are defined in the LVLH frame, while the Chief's orbit, in terms of position and velocity, is defined in ECI frame. Therefore, we must convert the coordinates from ECI frame into LVLH frame, apply these algorithms, and then convert them back into ECI frame to accurately model the orbit. One of the key parts of this algorithm is to determine how often corrections will need to be made in order to maintain the correct orbit. Long intervals will result in loss of data due to the drift between the two spacecraft caused by the perturbations. But short intervals will result in wasted fuel for adjustments that are not necessary yet. So it was decided that the corrections will be made roughly once in orbit to maintain these orbits while also not costing exuberant amounts of fuel. Because the orbits are modeled using relative orbital elements, the maneuvers that will be performed by the spacecraft to readjust the orbits will also have to be written in terms of these relative orbital elements. Because of this, we'll be using a linear motion model for the inclusion of these maneuvers in relative motion. The image in the bottom right shows how these spacecraft maneuvers will be represented using relative orbital elements. Due to errors in modeling the orbits in relative orbital elements, this portion of the project has not yet been completed. Because we need to be able to accurately model the orbits using relative orbital elements to test whether or not the PRA maintenance algorithm will actually function correctly, we have not been able to test the functions that have been developed. This part of the project is ongoing. Once the bug in the code has been fixed, then the project will be able to progress further. I would like to give a special thanks to Dr. Sunjo Chung and Kai Matsuka for assisting me in my surf this summer in the ARCL. I would also give a thanks to Toshi Kubota Aeronautics for funding my surf. Thank you.